I'm Liz Payton with Western Water Assessment at the University of Colorado Boulder, and thank you for joining us. We'll be providing an overview of our recently released user guide to snowpack monitoring in the Rocky Mountain West. Before we get started, a bit about Western Water Assessment for those of you who have not worked with us in the past. Western Water Assessment is an applied research program that addresses societal vulnerabilities to climate variability and climate change, particularly those related to water resources. We're based in Boulder and Salt Lake City and work across the Intermountain West, Colorado, Utah, and Wyoming. Western Water Assessment is one of 11 teams in the NOAA Regional Integrated Sciences and Assessments, or RISA program. Our speakers today are Karl Wetlaufer and Jeff Deems. Karl is a hydrologist and assistant supervisor for the Colorado office of the USDA NRCS Snow Survey and Water Supply Forecasting Program. Jeff is a scientist with the National Snow and Ice Data Center and one of the founders of the Airborne Snow Observatory, or ASO, team. And he's a longtime research collaborator with Western Water Assessment. Both Karl and Jeff were early reviewers of the user guide. We appreciate the time and effort they've put into the guide and speaking to us today. The presentation will be recorded and last about 45 minutes, followed by Q&A. Please feel free to submit questions via the Q&A window. We'll be sure to share a link to the recording with you after the webinar. I'm going to hand it off to Ethan Knight, a researcher with Western Water Assessment, who will give a brief overview of the guide before Karl and Jeff dive into the details.
Thanks, Liz. All right. The Snowpack user guide was written by a team at Western Water Assessment led by Leniko Wolders, who is currently on maternity leave, and Jeff Lucas, who is now the principal at Lucas Climate Consulting and Research. I hope you both are watching. Our team assembled this guide for water managers, decision makers, forecasters, researchers, and others who use, collect, and produce snow information. The guide is organized around 5 objectives. 1, to outline the fundamental characteristics of the snowpack, the processes that drive its variability over time and space, and the challenges of sampling such a dynamic resource. 2, to highlight the key role of snowpack in seasonal water supply forecasting. 3, to describe snowpack telemetry, or SNOTEL, snow course and other point networks of point observations. 4, to summarize the several products providing spatial estimates of snowpack derived from point observations, snow models, and remote sensing. And 5, to provide practical guidance on accessing, interpreting, and applying snow data. In the Rocky Mountain West, snow is a dominant player in the hydrologic cycle. Across the states of Colorado, Utah, and Wyoming, where Western Water Assessment focuses its work, most of the region's annual stream flow, about 60 to 85%, originates as snowmelt. The region's snowpack is effectively an enormous seasonal reservoir that fills and then empties every year. Monitoring the evolution of the snowpack over the course of the winter and spring is critical to forecasting stream flow and managing water supply. Snow monitoring is also vital to other river-based interests, such as fisheries management and guided rafting. So, how do we know how much water is in the snowpack? The depth, density, and areal extent of the snowpack changes over time, making answering this question particularly challenging. The metric most commonly used to integrate snow depth and density, and thereby express the amount of water contained in the snowpack, is snow water equivalent, or SWE. SWE can be thought of as the depth of water that would result if you melted a column of the snowpack. All climate models project that the recent warming trend for the region will continue, if not accelerate, depending on the trajectory of greenhouse gas emissions and uncertain feedbacks in the climate system. Due to this continued warming, future hydrologic projections for the Rocky Mountain region show a strong tendency toward future declines in April 1st SWE, despite modest projected increases in winter and early spring precipitation. This strong tendency towards decreased April 1st SWE reflects multiple effects of the projected warming. A shift toward precipitation falling as rain instead of snow, greater sublimation and melt of the snowpack throughout the season, and a shift toward earlier snowmelt in the spring. These warming-related effects are strongly modulated by elevation, with snowpack at higher elevations seeing less impact from warming as a percentage of current snowpack than at lower elevations. The general mid-range of the projected change in April 1st SWE by mid-century is a loss of roughly 10 to 20%. These declines in SWE are expected to be greater by mid-century at lower elevations in the snowpack zone, at roughly 8,000 to 10,000 feet in Colorado, and in southern parts of the Colorado River Basin, where the winter climate is not as cold, the snowpack is shallower, and the snow season is shorter. Even at higher elevations, such as above 11,000 feet in Colorado, spring snowpacks are expected to decline. The last section of the guide presents many sources of snowpack data and provides practical information to help users navigate and retrieve such data. Karl and Jeff are here to describe and demonstrate some of these tools. And with that, I will hand it off to Karl. Thanks.
Okay, can you see and hear me there?
Yep.
Okay, I'm trying to get it into presentation mode real quick.
Okay.
All right, thank you, Ethan and Liz, and thanks for everyone for attending. And yeah, we're definitely happy to be here to provide a little supplemental information. So hopefully this additional overview is useful and can help people utilize the data to the best capability. So I wanted to start just with kind of an overview of the history of Western snowpack monitoring and just kind of move up to where we are with the current state. And then Jeff will get into kind of some of the newer technologies. So Western snow surveying kind of started in the early 1900s near Lake Tahoe. The good Dr. James Church, who's actually a classics professor, has an interest in science and wanted to develop a way to forecast the future elevations of Lake Tahoe and then the outflow to the Truckee River. So he actually started developing just on his own the same modern techniques we use for snow course measurement today. And that includes both the technique of measuring a transect as well as the basic equipment, which has advanced a bit, but he was the start of it. Then shortly after the Dust Bowl in 1934, it was recognized the importance of snow as a water resource to the West, and federal funding was provided to initiate a snow survey program. It was in 1936, after a little research was done and measurement locations were identified, the official federal, state, and private cooperative snow surveys began across the West. This program has always been run under the USDA, and the NRCS has had several names over the course of time, but it always has been a cooperative program with people with a vested interest also helping to measure the snowpack. Many of these snow courses are still measured today. I know we have countless here in Colorado that actually do go back to those original 1936 snow courses and still do provide very valuable information. For those who are not sure exactly what a snow course is, it is a transect, commonly 5 to 10 points, where we take a core of the snowpack and we actually weigh that core. And that provides us the best measure of what liquid water would melt out of that column. It's a way to take out the effects of density. So regardless of snow depth, if you have the weight of that snowpack, that can give you the direct measure of liquid that would actually melt out. The measurement intervals vary state to state. Here in Colorado, we measure first of month, February through May. In some other states, such as Arizona, they also do mid-month measurements. So the manual snow course process went on for about 30 years before we really started looking into automated stations that eventually turned into the SNOTEL. So in 1964, the first instrumentation, which would be the first snow pillows, started being experimented with, but there was no telemetry to actually get the data out in real time. So staff would actually have to go up and download the data, which back in the day, download would be grab a scroll of paper most commonly. And then throughout the 1970s, we began experimenting with different telemetry types to figure out what would work best. And that data became, quote, real time, but it took a while to actually be able to get it dialed in where we were getting full 24-hour measurements. And even after the initial official SNOTEL network came to be. It took a while to get that ironed out. But the current SNOTEL system, as we think of it, officially began around 1977 and 78 is when there's a really big push to get sites in the field that would be able to be telemetered in real time. And again, in those days, pre-internet, it was really only the offices, the snow survey offices that would have access to that data, but then the time series would be available after the fact in monthly reports. These commonly replace snow courses, with the SNOTEL being co-located for commonly a period of at least 10 years. But there's also many, many times where it's just a brand new location that's been identified for a specific purpose or just to fill a gap in a watershed or mountain range. So SNOTEL sites were originally and still primarily funded for water supply forecasting and largely for agriculture. But the data really gets used for a wide variety of reasons these days, from avalanche centers, the Weather Service, variety of state agencies, recreation, from a personal standpoint, recreation businesses. But they all find this data we collect quite useful. So every SNOTEL site in the network measures snow water equivalent, which Ethan described. And I'll go into exactly how these measurements are taken in a minute. The snow depth in whole inches, the accumulated annual precipitation, which naturally you can break that down into smaller chunks, but the primary thing we measure is water year precipitation, so October 1st through September 30th, and air temperature. Then we also have a variety of enhanced SNOTEL sites. Many of them, the most common enhanced sites have soil water content and soil temperature, and then quite a few have relative humidity, wind speed and direction, as well as solar radiation. And across our network, we are looking to increase those parameters. And leading into Jeff's talk, a big goal of that, with things like solar radiation and the other parameters, is to be able to support spatial modeling better and work together with the different communities to get more in situ data to drive spatial models. So here's an example of a relatively classic looking SNOTEL site. We pretty much always try to site them in meadows within forested areas. And the primary reason for that is to reduce the risk of wind drifting. And that just leads to better comparability year to year if there's not effects on the wind pillow and the precipitation gauge from big wind events. So they're generally in these small protected meadows for comparability year to year. And then so for the infrastructure in the bottom left here is our snow pillow. And you can basically think of that as a 10-foot diameter rubber bladder that's filled with 150 gallons of fluid. Then how it works is it's plumbed underground into our shelter. And then there's a vertical manometer tube in here with a pressure transducer on it. So the more weight of snowpack pushes on the pillow, it forces fluid out and up. And then we're basically weighing the snowpack secondhand. So it's not dissimilar to the snow course in that manner, as we're getting the water content basically from the weight of the snowpack. Then right above it, we have an acoustic depth sensor. So how this works is it emits a series of clicks and then measures the time it takes for the sound wave to hit the surface and be received, and then it can calculate the snow depth from that. Also on this tower are air temperature sensor and a radiation shield. Then over here we have our storage precipitation gauge, which functions very similarly to the snow pillow, where it's also plumbed into the shelter with a manometer tube. But instead of fluid being forced out, it's basically an open system. So the height of fluid in the gauge is going to be the same as in the shelter. And then we're able to measure the inches of precipitation down to a precision of 1/10 of an inch. Then we've got all our electronics in here, data loggers, a variety of other things. Then on the tower here, we've got our radio antenna and solar panel. All the sites are completely independently powered by solar and batteries. And this is a meteor burst antenna, which is our original system, but there actually is also recently a push to modernize to cellular and satellite telemetry. So here's just a view of the SNOTEL sites and snow courses in the Upper Colorado Basin. It's kind of hard to see, but the light dots, light colored blue dots are snow courses and the dark blue are SNOTELs. So currently 153 SNOTELs and 64 snow courses in the Upper Colorado. So now getting into how to access the data. There's a couple different ways, but the National Water and Climate Center based out of Portland is a great resource to access data statewide or westwide. And then we also have state-specific websites, which I'll touch on a little bit later, but I'd kind of want to focus on some of our more modern tools. So I'll go into these in more details, but some of our newer ones, interactive map, interactive charts. Here to the right is our update report, which may not be as fancy as the other ones, but it is a great one-stop shop just to get a quick view of basin conditions, or if you're interested in a specific SNOTEL site. So these tables are updated daily. Then we've got our report generator, help with our web services, which is a bit more of a technical way to access it, but if people want really specific data or larger data sets, I'm going to leave the streamflow forecasting for the next webinar, but a lot of information on our streamflow forecasts, as well as links to the state-specific snow survey websites. So a lot to explore. So diving in, I'm going to spend really most of the time on what we're calling our interactive map. It's really an excellent resource for pretty much all data we have in our database. Several different snowpack parameters, precipitation, reservoir storage, streamflow forecasts, observed streamflows, and soil moisture. And I won't dive into the second half of that literature too much because I'm going to go over all of it. But yeah, station as well as basin summaries, access to different types of tables and graphs, custom visualizations, an export function where you can have a more cartographically correct graph that if you want to present it, as well as you can download a CSV file for further analysis. So here's just a quick tour of the interface on the interactive map, and I'll just kind of go left to right here. The bottom left is obviously the legend, but important to note at the top of the legend, I'll always display exactly what parameter you're expressing. So that's always good to double check as you're analyzing things, just to make sure you didn't accidentally click the wrong statistical parameter or accidentally change the date. So that'll always tell you exactly what you're displaying. Up here, we've got this, it'll have the drop-down menu of the selected stations. So you can select a display by HUC. So I just identified just the HUC for the Gunnison River Basin. So it's only 16 SNOTELs. And in this menu is also where you can download that CSV file. And that's pretty cool because it doesn't only download the parameter you're displaying. For instance, here's the snowpack percent of median, but it'll have all 15 or however many statistical parameters we have available for that station and that day for a lot of different types of analysis. Then top center here is where the print export function is, and that's where you can download a more detailed just more cartographically correct map for presentations in several different formats. And then this is just the main control menu, and I'll go into a little bit more about that now. So there's a lot going on here. Don't want to beat it to death, but basically you can choose what environmental element you want to look at. Lots and lots of different statistical parameters, you know, your standard averages, medians, but then there's percentiles, ranks, records, tons and tons of different ways to look at the data. They naturally select the date or date range. In here, you can compare to any custom period of record. You're not just locked into our standard 30-year quote normals. You can compare to any year to year you want. And then this bottom section is more for the cartographic display. You can select your own color ramp, range of the legend, transparencies. So if you're making your own, even for your own viewing, or if you're making a map to present to others, there's a lot more control now to make a cartographically correct map or just have it display as you want. The last main thing I'll mention here is one of our newest additions are these sub-basins, where we've gone through and identified on a smaller scale basically you can think of it as a larger HUC, which stations are most appropriately represent which basins, and it has allowed us to refine into smaller basin summaries instead of having to look at one number for the entire Upper Colorado or entire Gunnison. Now they're split into smaller basins. We hope will be useful for local water users or other entities. Last thing here, at the very bottom, there's probably a dozen different base maps, different topos, area or satellite imagery. You can have, these are watershed boundaries if you want to just put the watershed boundary on, but not have the basin summary. And then you can label names, parameters, HUCs, elevations, and have all that display for the station and basins. So in addition to just displaying it visually on the map and having the brief labels, you can also click on individual stations and individual basins, and then there's a pop-up with a ton more information. What we've had for a long time is a lot more summary statistics here. Not going to list through them, but tons and tons of additional summary statistics. And then more recently, we also have a quick link to the interactive graph, which so you can see the time series, and then you can also compare to any period of record, which I'll mention a bit more in a second. But a ton more information if you click on individual stations and basins now. Here's just a few examples. So this is delta value, so you can identify change over time for several different of our parameters, and you can identify any period, 1 day, 2 days, 5 days, literally any period you want. So this is an example of a 2-week change in SWE in the SNOTEL in the Gunnison Basin. So really cool way to look at the data, not only from a water use standpoint. I know backcountry skiers like that to see where things are going and or where not to go, perhaps, if it's an avalanche concern. This is another interesting one. You can look at how a given parameter in a given year, what its percentile is compared to the period of record. And this is useful for a lot of reasons, but I think one of the biggest, most powerful things about the interactive map is with the ability to compare to any period of record. So this is going back from May 1st, 2020 to current. It can better express how dry the summer really was, and it paints a different picture than just looking at water year precipitation. So, which can be kind of limiting because just looking at water year precipitation might provide a rosier picture of our current drought situation and potential runoff. The last example here is just wanted to show our sub-basins where historically a lot of our products would have been the entire Gunnison Basin with one number. Now we have these more refined sub-basins, which we really hope will provide better information for local water use. I mentioned our interactive charts. Another new product. The biggest thing here is just the ability to compare to any period of record. You can go and click. So if you can think of analogous years, if you say this year's dry and you wanted to see how it compares to 2002 and 2012, you can easily just do those quick comparisons. This is what we call a projection plot, where the black line is our current data, and then it provides different exceedance probabilities, basically. So you can get a range as the season progresses of where things may end up by different probabilities. Last thing I can mention, there's this slider on the bottom where you can pick what range and it'll zoom in on any time period. If you want to look at just a particular weekend storm or something of that nature, you can use that slider to zoom in on any time period to better quantify increases or decreases. So the last main kind of interactive tool through the Water and Climate website that I'll mention is the report generator. And this is a very, very powerful tool. This is something where you can pull a lot of data, organize it just how you want. You can add, and this has access to snow data, reservoir, all sorts of different things. You could add individual stations you want, or using the advanced search, you can easily pull all base stations in a state, all stations in a particular county. Also has a lot more parameters that are available in other tools. Just a lot more metrics you can look at. Even down to, we have our radio battery voltage and all sorts of stuff. So it's a little more in depth, but you can make a lot of good custom products. And one good way to get started here is if you click on a station in the interactive map, you can get a link to tables or charts in Report Generator for an individual station, and then you can use that base to add stations or modify as you wish. So the other main way to access SNOTEL or snow survey data in general is through our state snow survey pages. So all 14 Western states have their own individual snow survey pages. We do, I think pretty much all of them will have links to all the more interactive products I was just showing. But in addition to that, there will be more local custom products that I think a lot of people are used to seeing, just the standard maps that come out of ArcGIS and just kind of Excel graphs. But a lot of states will have more custom products that may be of interest. Other big thing we offer, which I'll touch on in a minute, is our water supply outlook reports are available through the state pages. And I believe the Climate Center site has those links as well. So I'm not going to go into depth. I know I'm sure we've got 40 or more different daily products we produce out of our office here that are similar to these just static maps and graphs. So I'm not going to beat this to death too much, but very worth exploring our website or other states' websites of interest, because there's tons and tons of different information that you may find useful, or you may be useful in a different type of presentation or something like that. So the last thing I will mention here is our water supply outlook reports are probably our most formal output of data, and they're a great one-stop shop for basically monthly water supply conditions from all standpoints. We both give a statewide summary and individual basin summaries of current snowpack, precipitation, reservoir storage, and our official water supply forecasts. And those include the tables where it gives 5 exceedance probabilities and really the most information possible. And through our Colorado Snow Survey website, you can sign up for email alerts where when we produce this monthly report, you'll get an email and you'll be able to access it online and download it from there at will. But it's about a 40-page report with kind of more specific summary text, lots of maps, graphs, really a great resource to just get the whole big picture. Yeah, and these again are also produced individually by all Western states and Alaska. So that is all I had, and I will pass it on to Jeff.
Great, thank you, Karl. Okay, so I'll dive into the remote sensing and spatial modeling portion of this, recognizing up front that this topic could easily consume a semester-long graduate course or even an entire career. We'll skip across a couple of highlights for some context, and then a little more specific details on some of the techniques and products mentioned in the user guide. Oops, click. So snow remote sensing. Basically, we can conceive of a couple generalities. Those are active and passive instruments. So active being instruments that send out a signal and measure the backscattered energy from that signal, and passive sensors just looking for either reflected or emitted radiation coming from the Earth's surface or atmosphere. And then the different platforms that those instruments can be on. I'll talk about airborne and satellite here, but that spectrum certainly includes UAVs and even ground-based like tripod-mounted sensors with similar technologies. Some of these sensors and techniques are snow-specific. Others are slightly more indirect measures of the seasonal snow cover, and yet others provide signals of opportunity that were designed for something else, but that we can leverage to retrieve snowpack properties. All of these methods require some level of calibration or model integration, some extensively, some less so, and I think you'll see some of that flavor here. Looking particularly at active sensors, there's basically 2 kinds of those. Those are a microwave or radar sensors, and LiDAR, which is a laser radar. In the microwave radar sensors, typically it's either a timing or some sort of temperature, timing or properties of the backscatter radar signal. They're evaluated for retrieving things like SWE directly or depth and density. We can also see layering or just the height of the snowpack, all of these depending on the radio frequency that's used and partially on the state of the snowpack itself. Some really promising results coming out of the radar community these days, including the ongoing, in fact, even probably live in the field today, NASA SNOX campaign. However, to date, a lot of these techniques have struggled to deal with wet snow or in rough terrain or rough ground surface or in forested environments. Primarily these sensors are used in a research and development mode these days. LiDAR primarily measures range to target and therefore can be converted into a surface elevation measurement. There's typically some property of the reflected laser signal that comes back as well, like reflectance, that can be analyzed, but the surface elevation is primarily the measurement of interest. Snow depth is retrieved nearly directly from this by measuring a snow-free surface and then measuring the snow-covered surface at a later date and subtracting those elevations. And importantly, this technique can see through the forest canopy, mapping not only the forest structure, but the ground or snow surface elevation beneath it. On the passive end of the spectrum, passive microwave, so same or similar radio frequencies to radar, but just looking at naturally emitted radiation. These sensors are, there's a network and legacy of them on spaceborne craft that were designed for other purposes, but the snow water equivalent emits a signal that we can try to measure. This is done typically over a large footprint, 25 kilometers square about, and it tends to struggle with rough terrain or deep snowpacks. And by example of that, the glob snow algorithm, with an example in the lower right here, is a global product that works well in the tundra and taiga and prairie environments, but they actively mask out the mountains due to the complexities in retrieving passive microwave signals from those environments. Useful from a global perspective, but less so targeted at mountain watersheds. Optical sensors are pretty much exactly what it sounds like, operating in the visible and near infrared, so the shortwave part of the electromagnetic spectrum. Typically looking at reflected sunlight in either several, like a multispectral instrument, or a continuous set of wavelength bands, like a hyperspectral or imaging spectrometer sensor. And these instruments can be used to map snow-covered area, or SCA, so snow presence absence in effect, as well as albedo, or the reflectivity of the snowpack, and other surface properties like the grain size, surface grain size, and any impurities or dust that are on the snow surface. A third technique measures gamma radiation. So this is naturally emitted gamma radiation from radioactive decay within the Earth's crust. That signal is attenuated by the presence of water. Pre and post snow cover flights can be used to estimate the amount of snow water equivalent. And that's typically done integrated over an entire flight line. So as we zoom in a little bit on some primary remote sensing products, these are ones highlighted in the Snow User Guide reports and are available for either operational or research to operations studies in the Western US. I'll focus primarily on the MODIS and MODSCAG algorithm, as well as the ASO data. But certainly worth a mention is the National Operational Hydrologic Remote Sensing Center's gamma radiation flights, which you can see a number of flight lines in Colorado illustrated by the little black squiggles on the center map there. Those data are used as a primary data assimilation source for the SNODAS system, which I'll mention in the snow modeling component of this. The MODIS sensor is a multispectral optical sensor. There's actually two of them on the Terra and Aqua satellites, so we get a twice daily measurement of surface reflectance from those instruments. They can retrieve fractional snow covered area, so what portion of each pixel is covered by snow, as well as grain size and albedo. The primary algorithms out there are the MOD10A1 primary product, as well as the MODSCAG algorithm produced by JPL. There's also a complementary algorithm to MODSCAG called MODDRFS, which measures the dust radiative forcing, so the reduction or the increase in absorbed solar energy into the snowpack due to the presence of dust or impurities. As I mentioned, there's a daily or twice daily repeat with both MODIS sensors, and typically a 500-meter pixel size for those. The NORSC gamma flights, as I think I mentioned, are a single SWE value for each of those flight lines. Airborne Snow Observatory is a paired airborne LiDAR and spectrometer combo. The snow density model it uses to get from snow depth to SWE is constrained by the measured airborne snow depths, as well as in situ observations from SNOTEL and other measurements. And this program produces snow depth and albedo at 3-meter resolution and SWE at 50-meter resolution for select full river basins in the western US. So we'll dive into a couple of these in more detail. The MODIS sensor, as I mentioned, is a multispectral sensor. You can see on the sort of middle right there, the 7 shortwave bands on the MODIS sensor, 3 in the red, green, blue visible, and then 4 others out in various infrared wavelengths. From those measurements, the surface properties can be retrieved, and the relative fraction of each of these various land cover types, so vegetation, trees, shrubs, grass, snow, soil, etc. The relative fraction of those in each pixel can be retrieved using a spectral unmixing algorithm. This method of measurement builds on a long legacy of optical sensors, AVHRR, Landsat, Thematic Mapper, and it's been around since the turn of the century, so it's an aging instrument at this point. Fortunately, we have a number of successor instruments making similar measurements, like VIIRS, the OLI, and the Sentinel satellites. The MODSCAG and MODDRFS algorithms are in use by a number of ongoing modeling efforts, particularly the CU SWE product, which I'll talk about in a bit, as well as the Colorado Basin River Forecast Center looking to incorporate dust forcing into their models. These products, particularly the MODSCAG product, produce fractional snow-covered area and optical grain size and albedo. One example of that spectral unmixing to retrieve the snow-covered area and grain size is this image from April 1st, 2005, showing the Sierra Nevada in California, and the multispectral signal can be unraveled to make that center map, which is the pixels that are snow, vegetation, and rock, and then each of the snow pixels can be further classified to retrieve that optical grain size, which is a primary driver of the albedo. The Airborne Snow Observatory, again, airborne platform and program, started at the NASA Jet Propulsion Lab and recently transitioned through a NASA Tech Transfer program to Airborne Snow Observatories, Inc., with a lot of the same staff, including myself, that jumped ship from JPL to continue this program. ASO maps snow depth and water equivalent and snow albedo using the paired laser scanner and imaging spectrometer. Those measurements are combined with physical modeling of the snowpack for snow density evolution, and the data are collected in a unique and optimized airborne flight program that enables rapid product turnaround within 72 hours of flight. To get to snow depth and SWE from these paired instruments, basically the aircraft mows the lawn over an entire river basin, as shown by the little video here. This is actually ongoing right now in the Tuolumne River Basin in California. The surface elevation maps are then differenced to get a 3-meter snow depth. That subtraction is constrained by the spectrometer retrieval such that all zero depth or no snow locations truly resolve zero and remove any bias. Snow density is measured by SNOTEL sites and also manually, and that's used to constrain the iSnowbow model, which is run and also constrained by the ASO measured snow depth. Depth times density gives us water equivalent at 50-meter resolution over entire catchments. This program has been primarily in California and Colorado since 2013. California has seen over 320 snow cover flights since then in 10 basins in the central and southern Sierra, and is by now essentially an operational program in California with full state coverage anticipated within 5 years, if not sooner. In Colorado, there's been a number of primarily project-based applications of ASO data, including all the basins and areas that you could see in the map on the right. With diverse set of funding, research funding from NASA and research to operations funding from Colorado Water Conservation Board and operational work with Denver Water, including ongoing projects this year. There's also the Colorado ASO stakeholder program that's working on defining a sustainable statewide program for ASO. So I recommend checking out their content at coloradoasoplan.org there. So shifting from remote sensing into spatially distributed SWE modeling, it's not a clear break there because a lot of these products leverage remote sensing observations as well as a lot of the measurements that Karl was describing. I'll briefly discuss these 4 systems here. Snow 17 is the snow component of the operational snow model run by the NOAA River Forecast Centers. It's coupled to the SAC-SMA hydrology model to produce streamflow forecasts. This is a lumped or semi-distributed model, so it runs an entire river basin like the Taylor River there at the bottom left, but broken up into several elevation bands to distribute SNOTEL precip into an elevation-dependent snowpack. The SNODAS or Snow Data Assimilation System is run by NOAA Office of Water Prediction. It's a 1-kilometer model run over the entire continental U.S. It assimilates the airborne gamma measurements that I mentioned previously, as well as pretty much any other measurements that are out there. So Weather Service co-op stations, SNOTEL data, AVHRR optical satellite measurements, et cetera. That program produces daily US-wide snow water equivalents, as well as other snow properties maps. The SWAN and University of Arizona program is a similar program run at 4 kilometers over continental US. It uses a slightly different method of interpolating and modeling SNOTEL data to a nationwide grid. And then the CU SWE project or program at the Institute for Arctic and Alpine Research here at the University of Colorado is based on MODIS retrievals of snow-covered area and other terrain parameters, and I'll get into that more in a second. A little more detail on the River Forecast Center's Snow 17 model. Again, there's multiple elevation bands in each river basin. The river basin is defined by forecast points on streams. Leveraging SNOTEL measurements of precipitation and temperature lapsed into various elevation bands. That snowpack is then fed into a temperature index melt model to provide snow melt in parallel to any rainfall inputs to the SAC-SMA hydrology model. That model is run in various modes to produce operational 5-day peak and seasonal water supply forecasts. I'll particularly recommend the CB Colorado Basin River Forecast Center websites with just a wealth of information and products in real time from this system. The SNODAS system, as I mentioned, produces 1 kilometer daily estimates of water equivalent snow depth, snow melt, sublimation, and snowpack temperature across the continental United States. And it's retrievable in a number of different formats. of particular utility is the long-term data set and the long-term observation network represented by the SNODAS system, such that it is a common reference data set for comparison and benchmarking, which is a really important component of comparing and developing new capabilities. Relevant to Colorado is the Colorado Decision Support System SNODAS tools that aggregates SNODAS data into river basins within Colorado, easily retrievable and interrogatable there. So a pretty cool tool to play with for local data. The University of Arizona product, as I mentioned, is run at 4-kilometer resolution and uniquely uses snowfall from Weather Service co-op stations to scale the PRISM precipitation products and extrapolate SNOTEL nationwide. That 4-kilometer product is refined using machine learning algorithms to a 1-kilometer product that's accessible through the SnowView application with the link at the bottom right there. And so that's a really interesting tool to explore, not only showing the current modeled snow water equivalent, but also the current SWE anomaly based on back calculation of these parameters back to, I think it's 1981. So you can look at that kind of percent of normal on this 1-kilometer grid. So
Jeff, you have about 2 more minutes.
Awesome, I'll speak even faster. The CU SWE product is also a regression model relating lots of terrain-focused independent variables to snow water equivalent. The really unique component of this model is that they use a library of reconstructed snow water equivalent. So that SWE reconstruction is basically running an energy balance model backwards, knowing the date of snow disappearance as detected by the MODSCAG algorithm. One can reconstruct how much SWE must have been on that pixel in order to produce melt out on that observed date. So that library is used in the regression to improve the spatial pattern prediction of SWE across mountain range scales. This product is produced for the Sierra Nevada and Intermountain West throughout the year on a near real-time basis within, I think it's 3 days of the MODIS overpass. Here's an example of one of their SWE reports from 2019. And again, there's a link at the bottom here, and this presentation will be posted to go check out some more of those products. I'll breeze through a couple of examples from the Colorado and the Upper Gunnison Basin here, just to kind of highlight some of the differences in these products. So that you probably can't see very well, but the Crested Butte's basically the center of this Africa-shaped East River Basin in the center of the image. This is the SNODAS SWE retrieval from April 7th, 2019. Moving forward, here is the 4-kilometer University of Arizona product, the CU SWE product from April 1st, and the Airborne Snow Observatory product. So we can see a lot of differences. Primarily resolution leaps out immediately, both spatial and temporal. But also implicit in all of this is differences in the model type and forcing data, and also the underlying observations that drive it. Zooming in a little bit is the same products in that order. So SNODAS, University of Arizona, CU SWE, and ASO. Zooming in a little bit more on the ASO products from this date and basin, just to give you a sense of the amount of variability that we're trying to simulate with all of these products. We can see at the large perspective some typical perspectives or typical patterns that we'd expect, like increasing snow with elevation. As we zoom in a bit, we can see that there's a lot of seasonal snow processes like wind, melt, and avalanching that produce a very complex pattern that really speaks to the challenge of sampling and measuring and monitoring these environments and producing hydrologic forecasts from them. So I think the main thing I want to summarize with here is that we are in an era of what we like to call the spatial revolution, where we're seeing remote sensing and modeling products become more available for operational uses. All of them leverage the observational legacy and the infrastructure from the NRCS SNOTEL network. So there's no sense of replacing those measurements. Indeed, they're fundamental and core to all of these approaches. We're seeing broad, regular spatial coverage from national investments in modeling and remote sensing measurements, as well as new developments, prototyping and refining these to support operations in parallel with the expansion of targeted higher accuracy airborne measurements. So in the future, again, this station network that Karl mentioned, along with forthcoming enhancements and expansion, will remain a backbone of our observation capabilities. Airborne systems are likely to provide key regular snow observations at high resolution. Current and emerging satellite data products add a global and temporal component. And really all of this revolves around the ability to support and drive physical modeling systems to improve our capacity to simulate and forecast river runoff. Thanks.
So if you could unshare, there you go. Thank you. That was fabulous, both of you, really great. Okay, let's do this, go back to this, and okay, so thank you so much, Ethan and Karl and Jeff. Those were really great presentations. And thank you also to everyone who has submitted questions through the Q&A box. Please feel free to keep those coming and we'll answer questions up until about noon. So we did get one question via the email, and I'll just read that one off so we can get that one taken care of. To what extent do data providers either remotely sense snow products or in situ products like the SNOTEL sites consider and provide estimates of uncertainty with their data products? And is there any guidance on how the end user might estimate uncertainty when it's not provided for either point level SWE measurements or remote sensing products? So Jeff or Karl, would you like to help with that?
Yeah, I can get started. I mean, that's certainly one of the big challenges in snowpack monitoring in general is that difference between having a point in situ measurement and comparing that to a distributed model. And just from my area, it is difficult to estimate that uncertainty because it would require quite a few more ground truth measurements than can be realistic. And it's also a challenge because SNOTEL isn't necessarily designed to represent a greater basin. It can provide a metric, but since they're all in meadows, like the snowpack sitting in the middle of this open meadow isn't necessarily going to be the same under a dense canopy nearby. So, I mean, it's an excellent question, but it is really a difficult thing to quantify what that true uncertainty is without really extensive ground truth measurements from both in situ, like SNOTEL sites and from distributed models. But Jeff's certainly more the expert in the distributed side.
I'll agree. It's a really great question and one that I think is critical moving forward, especially if you consider data assimilation into more advanced models. A true data assimilation requires both a measurement of SWE or whatever surface property and an estimate of its uncertainty. It's difficult to come by, as Karl mentioned. With ASO, we've nailed down our uncertainty, we think, to a pretty tight range on the order of 2% SWE. There's a chain of calculations to get to that point. So I think we're seeing, well, one method of anticipating uncertainty in other data sets is comparison with ASO data. But again, there's no absolute zero uncertainty benchmark data out there with which to make this comparison. So I think it's something that will continue to be refined as each of these products progress.
Great, thank you. I have a question here for Jeff, and that is, with microwave radar, what do you mean by layering? Can one observe ice lenses or depth hoar?
Yeah, so there's certain radar frequencies and configurations of the sensor can actually retrieve returns off of intermediate layers in the snowpack. So different snow properties have slightly different dielectric constants, and that contrast shows up in the radar echogram. So yes, you can see things like depth or ice lenses. Doing that reliably in all terrain from air or space remains a pretty significant challenge, but it's certainly one of the appealing promises of radar remote sensing.
Thanks. Okay, here's a question. How many more soil moisture and wind gauges do you need to have a full understanding of these important parameters?
Well, we'd like to have as many as possible, ideally. And it's really depends on the type of modeling you're doing, and the spatial scale at which that model output is. Yeah, the short story is we'd like to have as many as possible, but a lot of it depends on the spatial scale at which you'd want to use that data to model. I'm sure Jeff could elaborate or be more specific.
Yeah, I mean, the cheap answer is we don't actually know, but it's kind of an iterative process where we can make remote sensing measurements and field measurements and feedback on the other to get a better handle on what the variability is, and the number of measurements needed is subject to how much variability there is in the parameter of interest. So it's an iterative process, and I think it really highlights the need for an integrated measurement and modeling system. So ground-based measurements with long legacy like Karl and the NRCS maintain, spatial measurements from remote sensing platforms, all integrated in a modeling environment that can handle it.
Okay, thank you. So we received several questions about runoff forecasting, and our second webinar is going to focus on that. So I'm not going to forward those questions on to our panelists, but I hope whoever's asking those questions will tune in on March 11th for that webinar. So here's another question. Is there any active discussion on changing from April 1 to a day in March, given expected climate changes?
I'm guessing that's referring to kind of the, an assumed or kind of standard assumption of peak snow water equivalent in the West.
Right.
And I'd say that it's kind of out of my area of expertise. We mostly focus on the monitoring and data providing side of things, but I would foresee that would be highly variable in different regions, that there'd be a different signal in Arizona versus the North Cascades or the Sierras over time. I could see that being variable just with different snow climates.
Okay. This one's for Jeff, I think. Can drones be used in the ASO program?
Yeah, that's a good question. Currently, drones can't really operate over the spatial scales that the ASO plane covers, though certainly drones with either the same or additional sensors like a radar could be used to provide higher resolution sampling that could inform the modeling as well. We'll see if technology and regulations allow much bigger drones to operate over longer time periods and bigger areas. Perhaps that's a possibility.
Okay, thank you. And we're just about out of time, but there was a question, and I don't see it now. It must be somewhere else. But about the current conditions of the snowpack in the Colorado River Basin. Did either of you want to offer a couple of words about what you're seeing right now?
I will let Karl start, since ASO has yet to fly in the Colorado River Basin this year. We'll start flying in early April.
Yeah, I can pull up just real quick.
Okay.
You know, it's a big deep dive within the state of Colorado as of the 23rd. So midnight 2 days ago, within the state, snowpack was at 90% of the median. With that being the best snowpack the only above normal is in the upper Rio Grande. Then the Arkansas, South Platte, North Platte are doing pretty good. Looks like the Southwest Mountains, the Southwest San Juans and the Gunnison are in the mid 80% of normal range. And the Colorado Basin, basically from Rocky Mountain National Park to Grand Junction, is at 88%.
Great. Thank
Whoever
you.
had that question, feel free to follow up and I can give more details.
Okay. Thanks so much. So it's noon now. So thanks so much to everyone for joining us. And thank you to Ethan and Karl and Jeff for their fabulous presentations today and answering the questions. Part 2 of our webinar will be, we'll cover applications of snowpack data, including runoff forecasting, and we'll send out an announcement and registration link early next week to that webinar. And remember, please, that you can download the full report and view other resources at the Western Water Assessment website. And Ethan has posted a link to the full report in the chat box. And we'll also be posting a recording of the webinar on our website and send you all a link when that's posted. And in the meantime, please feel free to reach out to any of us. This is our contact information if you want to keep the conversation going. Thank you so much.